In this lesson, we're going to look at oxidation numbers. The oxidation number of any element in a compound is basically defined as the charge that it has or appears to have. We know from studying elements on the periodic table that there are elements that can have multiple charges. So the oxidation number is simply the charge that it has in that compound. In order to assign oxidation numbers, we have to follow several guidelines. These guidelines are listed in the order in which you should approach the question. And we'll go through several examples in a few moments. But basically, when we're assigning oxidation numbers, we first have to ask ourselves, is it a free element? If it is, it has an oxidation number of 0. For instance, zinc by itself, because that's the way it appears in nature, has an oxidation number of 0. There's no charge on that. O2, oxygen, has an oxidation number or a charge of 0 when it's by itself. P4, S8, and so on. If it's not a free element, we then ask ourselves, is it a monatomic or simple ion? If so, the oxidation number is equal to the only charge that can have. For instance, chlorine, anything in group 7, has a -1 charge. Zn2 positive can only have a +2 oxidation number. Anything in group 1, like Na, is Na positive. It can only have an oxidation number of +1. And it's at this time that I want you to realize that when it's a charge, the sign goes after the number, like Zn2 positive. And when we want to identify what the oxidation number is, then the sign comes out in front, +2. That's the way that we distinguish between charge and oxidation number. Anything in group 2, like Ba2 positive, can only have a +2 oxidation number, and so on. Then we ask ourselves, is there hydrogen in this compound? And if there is hydrogen in this compound, we're going to assign it an oxidation number of +1, because that is the oxidation number that hydrogen has most of the time. There are some examples, or some exceptions, and those would be, for instance, sodium hydride, Na positive. In this case, hydrogen has a -1 charge. This is not really an exception that you need to memorize. The reason why you don't need to memorize it is, as I said, you have to go through the guidelines in order. And if we look at NaH, well, we're going to assign sodium a +1 oxidation number first because it follows guideline number 2, and we have to go in order. The overall charge on NaH is 0. There is no charge there, which tells me right away that the H, or the hydrogen, has to be -1. +1 and -1 makes an overall 0 charge. So you'll catch up on that if you follow the guidelines in order. You don't need to memorize the exception. Then, if we have oxygen present, we're going to assign that an oxidation number of -2, because that is the oxidation number that oxygen will have. Again, there are exceptions to this rule. For example, peroxides, like hydrogen peroxide. Hydrogen is at number 3 guideline, so we would assign that before the oxygen. So hydrogen would be +1, so the oxygen would have to be -1. The same thing as OF2. Fluorine is in group 7. That follows along with guideline number 2, so we would assign that as -1 each first. Oxygen has to be +2. Right now, this might sound confusing. We will go through some examples, but I wanted to hit on what the guidelines are and emphasize that you need to go through them in order. Like we talked about for the sodium hydride, the sum has to basically equal the charge. Right here we have an overall charge of 0, so all of the oxidation numbers must add to give us 0. If there is an overall charge other than 0, such as MnO4 negative, the overall charge is -1, so all of the oxidation numbers must add to -1. And finally, in a covalent compound, if it doesn't have hydrogen or oxygen, the more electronegative element is assigned its negative charge in that ionic compound. Meaning, if hydrogen or oxygen is not there, there's no monatomic, we go through all of the guidelines and we cannot assign an oxidation number. We look to see which one is more electronegative according to the periodic table, and we assign that the oxidation state of the charge that it would normally have, and then solve for the other one. At this time, I want to go through several examples of the guidelines, so I would like for you to turn to page 7 in this booklet to question number 3 in the worksheet. And I want us to go through part A, assigning oxidation numbers to all of the elements in the compound for carbonate ion. So the first thing, you need to look at what elements are there. And we have carbon and we have oxygen. And I want you at the same time to look at your guidelines. And I want you to start at number 1 and I want you to go down until you find a guideline that's applicable in this case. There are no free ions. There's no element here that's just by itself. Guideline number 2, any simple monatomic ions. We don't have any of those. We have carbon and we have oxygen. Then we look at guideline number 3, which asks us, is there hydrogen present? There is no hydrogen present. We go to guideline number 4, is there oxygen present? Yes, there is. Therefore, we're going to assign this an oxidation number of -2. Now that we've assigned that an oxidation number of -2, we must solve for carbon. And I find that most students find this concept a little bit easier when we denote what we're trying to find as X. So we have carbon, which we don't know what the oxidation number is, so we'll call that X. And we have 3 oxygens, and we know that each oxygen is -2. And all together, this must add to give the overall charge of 2-, or -2. Then this just becomes an algebraic question. We have x subtract 6 equals -2. We bring the -6 to the other side and it becomes positive. So we have x is equal to -2 plus 6. So x is equal to +4. Since x represents carbon, I know that carbon has an oxidation number of +4. And this question is complete. Let's try this again with part B. In this compound, we have potassium, we have sulfur, and we have oxygen. So let's go through our guidelines. There are no free elements. There's nothing here that stands alone. Do we have a monatomic or simple ion? Yes, we do. Potassium, or K, is in group 1. The only oxidation state that it can take on is +1. Guideline number 3, do we have hydrogen? No, we do not. Guideline number 4, do we have oxygen? Yes, we do. We'll assign that an oxidation number of -2. Once we have all of the oxidation states except for 1, we can set up an algebraic question. We have 2 potassium, so 2 times +1, plus 1 sulfur, which we don't know, we'll call X, plus 4 oxygens, and together that must equal the overall charge here, which is 0. So 2 plus X subtract 8 equals 0. X is equal to 8 subtract 2, bring those over to the other side. X is equal to +6. Therefore, sulfur must have an oxidation number of +6 in this example. Question is now done. At this time, I strongly encourage that you pause the video and I want you to go through and complete the rest of these, C, D, E, and F, as well as question number 4. Practice it. Open up the completed notes where you'll find the answers. Check, make sure you understand this before you go on to the next part of the video. We're now going to build on oxidation numbers by using them to identify if something is a redox reaction or not. By assigning oxidation numbers to all of the elements in all of the compounds in a balanced chemical equation, we're able to identify if an electron has actually been transferred or not. If an electron has been transferred, the charge that the element has in the beginning as a reactant will be different than the charge that it has as a product because it gave away or accepted a negative charge. Therefore, the oxidation numbers will change. You can see that in the first example. Oops, that's been done here for you. They've assigned the oxidation numbers to all of the elements in all of the compounds in this balanced chemical equation. So now an example is very similar to part A, B, C, and D that you just did. You can think of NaCl as part A, AgNO3 is part B, NaNO3 is part C, and AgCl as part D. Do them all individually. They've assigned the oxidation numbers, and hopefully you've done the worksheet at this point, you've checked your answers, and you understand it, so I'm not going to go through where these numbers came from. That should be evident at this point. In order to identify if it's a redox reaction, we have to look for a change in the oxidation number from that same element as a reactant and as a product. For instance, we have Na, which has an oxidation number of +1 when it's a reactant. When it becomes a product, it's still +1. Cl is -1 when it's a reactant and -1 when it's a product. Ag is +1 as a reactant, +1 as a product. N is +5 as a reactant, +5 as a product, and oxygen is both -2. Since there is no change in the oxidation numbers from reactants to products, this is not a redox reaction. Let's go through our own example. You'll notice in number 2, NO3 has been crossed out because if you were to go through and write out the total ionic equation and the net ionic equation, this would be a spectator ion. Therefore, we can also ignore it when we do this part of the question. Keeping in mind your guidelines and the fact that you need to do them in order, let's look at copper solid. Copper solid is on its own, and this is the way that it naturally exists in nature. Therefore, it's going to have an oxidation number of 0. Then we have 2Ag, and once upon a time, this was attached to the NO3. Therefore, it has a +1 oxidation number in this case, in order for us to do the crisscross from Science 1206. Notice we're only assigning oxidation numbers to the elements in the compounds. The coefficients, that 2 in front, is negligible, and we can ignore it. Then we have Ag solid on its own, and that's the way it naturally exists in nature. So it has an oxidation state of 0 or an oxidation number of 0, whichever phrase you prefer. And then we have copper. And we have copper bonded to NO3. And notice that when copper was bonded to NO3, we needed 2 of the nitrates. I did not manage to circle. We have 2 of the nitrates. Recall from the back of the periodic table that NO3 has a negative charge. If we needed 2 of them, it means that copper must have a +2 oxidation number or a 2 positive charge in order to make that valid. Now what we need to do is we need to look to see, has there been a change from when it was a reactant to when it was a product? Notice copper was first 0 and then it went to +2. So copper went from 0 to +2. And we had silver, Ag, and that went from +1 to 0. So the first thing, yes, this is a redox reaction. Then the question is asked us, if it is a redox reaction, let's identify what is undergoing oxidation and what is undergoing reduction. So let's look at copper. Copper went from 0 to +2. And what you need to ask yourself, knowing that electrons are negatively charged, did the copper have to give away electrons to go from 0 to +2, or did it have to accept some electrons to go from 0 to +2? And I want you to think about that for a second. In order for copper to go from 0 to +2, it had to shed some of electrons. It had to give them away, get rid of some negative so it can become positive. And remembering from previous, in the part 1 of the lesson, oil rig, if it had to give away electrons, this one is undergoing oxidation. For silver, it went from +1 down to negative. And in order to go down to negative, you have to accept or gain a negative charge. Therefore, this one is undergoing reduction. Let's look at example 3. We have zinc by itself, oxidation number of 0. Iodine, I2 by itself, oxidation number of 0. Then we have ZnI2. This is a compound, so we need to assign oxidation numbers. We first have to ask ourselves, is there anything by itself here? No, there's not. Do we have a simple monatomic ion? We do. we have iodine, and iodine can only have a -1 charge. Therefore, zinc, if you can set up an algebraic expression if you want. X plus 2 times -1 equals 0. And from there, it should be easy to see that X, or zinc, has to be plus 2. It's not necessary that you set up an algebraic expression. If you can figure this out in your head, that would suffice. Since there is a change, we went from zinc being 0 to plus 2, iodine going from 0 to -1. This is a redox reaction. Now we have to assign what's undergoing oxidation and what's undergoing reduction. We have zinc going from 0 to plus 2, and we have iodine, which is going from 0 to -1. And again, you have to ask yourself, does it have to gain electrons or lose electrons in order for this to happen? We look at zinc, it goes from 0 to plus 2. In order to become more positive, we have to give away or lose electrons. This is undergoing oxidation, and if one is undergoing oxidation by default, the other one has to undergo reduction. Otherwise, it would not work. And lastly, let's look at the last example, example 4. We have aluminum by itself, oxidation number of 0. Bromine, Br2, the way it naturally exists in nature, oxidation number of 0. Then we have Al2Br6 solid. There's nothing here that's by itself. Do we have a simple ion? Yes, we do. Bromine is in group 7. The only oxidation state this can have is -1. Therefore, we must figure out what aluminum would be. If you can figure it out in your head, fantastic. If you need to set up a algebraic expression, no problem. We have 2x, because we don't know what aluminum is, and we have 2 of them, plus 6 -1s has to equal the overall charge of 0. So 2x subtract 6 equals 0. Bring 6 to the other side. 2x equals 6. To get x by itself, divide both sides by 2. X is equal to +3. So aluminum here is +3. So we have aluminum that's going from 0 to +3. We have bromine, and that's going from 0 to -1. Again, ask yourself, do we have to gain or lose electrons in order for this to happen? Let's look at bromine first. We have 0 and we become more negative. Therefore, we had to gain electrons, so this is undergoing reduction. And by default, the other one is undergoing oxidation. Now that we've went through those examples, I would like for you to go through the examples in question number 6 on the worksheet.